Hello everyone! In this video I want to talk about one more example where we're going to use logarithmic differentiation to find f prime. Again, you don't have to use it because technically speaking you can see here a quotient, you will use quotient rule, you see a product, you will use product rule, and a chain rule as well. But to avoid doing this too complicated, we're going to use logarithmic differentiation to simplify the problem. So first step for logarithmic differentiation is to apply ln to the both sides, left hand side and right hand side. And let's write down what do we have. We're going to have ln of f of x equals ln of this huge fraction we're working with, which is x plus 4 raised to the 3/4 times x minus 3 raised to the 5/6 all over 3x plus 1 raised to the 2/5. And now you need to use properties of logarithm function. You remember that if you see a product inside of the logarithm, it will give you a sum of logs. So log that has a product inside will give you a sum of 2 logs. The log that has a quotient inside will give you a difference of 2 logs. Let's use this property right now. Left hand side stays the same, equals, and I will use both properties at the same time. What is staying on the top over here will be part of the first log minus the log of whatever staying in the denominator. But also whatever was in the numerator is a product. So I know that's going to be log plus log. I will show you what I mean over here. So I'm going to have ln x plus 4 raised to the 3/4 plus ln x minus 3 raised to the 5/6. This is coming from the numerator. You can even put parentheses like this. Since there was a product inside of the log in the numerator, that will give you log plus log. Minus, now I'm going to change the color, and it's going to be this part, ln of 3x plus 1 raised to the 2/5. So this is the part that comes from the denominator. Do you all agree with this piece? Log of the top minus log of the bottom, and the top gave me sum. I would simplify more. Every time I see the exponent like this inside of the log, I can move it down, or basically multiply by that exponent. So log will be multiplied by 3/4 in this case, 5/6 in this case, and 2/5 in this case. Let's rewrite one more time ln of, I will do blue color again. I will tell you later why. ln of f of x equals 3/4 times ln x plus 4 plus 5/6 times ln x minus 3 minus 2/5 ln 3x plus 1. This is the last time I need to simplify logs, which now I have. Let's see what we did from a huge fraction. Now we have just 3 little tiny logs with some exponents going on inside and outside. This should be easier to differentiate, and that's why logarithmic differentiation actually helps quite a lot. Finally, I'm starting differentiating only right now, step 4. So I use different color. The first 3 steps in blue we were using properties of logs. Right now, we're basically doing implicit differentiation. This is the implicit differentiation step. Implicit differentiation. So, I will differentiate both sides, remembering that f of x depends on x. So, every time I see f of x, when I differentiate it, it will have times f prime. ln of f of x, when you differentiate log, it will be 1 over everything inside of the log. That's a function f of x. Then chain rule says times, okay, look inside and check what's inside and differentiate that piece. So this is chain rule. Chain rule. So based on chain rule, I will have times f prime. I don't want to put it here because it takes too much space. So it's quite often you will see this piece going to the numerator. I'll rewrite it in the next step. Then it takes less space. Now 3/4 ln of x plus 4 will be 3/4 derivative of log 1 over everything you see inside of the log, x plus 4, plus 5 over 6 times derivative of log of x minus 3, 1 over x minus 3. Also, did I forget something? Let me check. I forgot to check if any chain rule should be applied here. Yes, chain rule should be applied. Every time I did 1 over x plus 4, next step will be times derivative of the function inside. But what is derivative of x plus 4? 1. That's why I did not really care about that, but I decided to mention right now. Same with the second step. 5, 6 times 1 over x minus 3 times derivative of the x minus 3, which is 1, minus 2/3 1 over 3x plus 1 times derivative of the function inside, and this time it's not 1, it's actually 3, and it's convenient to put it in the numerator. Now, this is really almost a prepared result, and as you can see, it's much easier than to differentiate everything using quotient, product rule, and chain rule at the same time. One of the last steps here will be step 5. I want to isolate f prime. So f prime or df over dx, whatever you like to call it, f prime of x equals. How to isolate f prime? Well, what is standing over here that is not allowing us to isolate it at the first place? At the previous step, we had f prime times 1 over f. That comes from the log. Well, let's multiply both sides by f of x. Both sides, left-hand side and right-hand side. Then we will have f prime of x equals the answer. Whatever is the answer, we can put in the answer part. Okay, so do you want to multiply by f of x? It is the correct step, and then it's still not quite a good answer though. Because in implicit differentiation, if you remember we were teaching you, f of x or y, if it's called y, sometimes is present in the answer. But in this case, f of x was given at the beginning. Look at this. F of x was given. Here it is. So it is important that we can use it for this type of examples when we work with logarithmic differentiation. This is how we're going to do it. I'll rewrite everything I had before, which was 3 over 4 x plus 4 plus 5 over 6 x minus 3 minus, well, 3 actually cancels out with 3 if I did not do any mistake, 2 over 3x plus 1, and then everything will be times f of x, and f of x comes from this piece. I can copy and paste it there, or let's just rewrite it. Becomes x plus 4 raised to the 3/4 times x minus 3 raised to the 5 over 6 all over 3x plus 1 raised to the 2/5. And this is the answer. Have fun typing this into your online homework, which is a mean joke, but I really wanted to make it. And just to point out, this is a very realistic situation when we use logarithmic differentiation instead of just differentiating the way we see it. For example, everything you know, which is done by computers, they take memory and time to calculate products and quotients, so it's actually quite often a very popular technique to use logs to transform products, quotients, and exponents into sums and differences. It's easier for computer to calculate, and it's faster. Every time you ask for example, Google for directions to some kind of place, it updates information fast enough that you can see the updates immediately. How is it possible that it is so fast? Because the code it uses has simplified products and quotients, and it's highly possible they use logs to do that. And they were finding derivatives using logarithmic differentiation.